Hey there, welcome to Learning Labs. Today we're in Geology 7. We're looking at Chapter 1, which is all about the composition of Earth. Check this out. This is flowing lava from Hawaii. After volcanic eruptions erupted and after the lava and the magma cools, it becomes like this black rock. It's called igneous rock. So Earth, what's going on? I want you to imagine something here for a second. So close your eyes, take a listen, all right? Imagine you're traveling to the center of the Earth. What would you see from surface to center? Would the journey take place in solid rock? Or would you travel through some layers of liquid or gas? What temperature changes might you notice? Humans are not able to travel very far under the surface of our planet. Scientists can predict, however, what Earth might be like at deeper levels. Some clues have been found in rocks and minerals on Earth's surface. Other clues have been found in the deepest parts of the oceans. The presence of lava and volcanoes show there is tremendous heat and pressure beneath Earth's surface. All scientific clues indicate that Earth is not a quiet, solid ball of rock. So check this out, Earth and its layers. Now, I'm gonna show you a cross-section, meaning a dissection of Earth's layers very soon here. Notice that there's 4 main layers, okay? You have your crust, mantle, outer core, and inner core. And you'll see some layers are liquid. Now check it out. We start here at level A. This is the center of Earth, as you may call it, which makes sense. It's the inner core. It's the deepest layer of Earth. Many scientists believe the inner core is made up of iron and possibly other elements such as silicon and carbon. The inner core is solid ball and it reaches temperatures about 5,000 degrees Celsius. As we move out, we get to the outer core. Now the outer core is probably made of liquid, okay? That's a hypothesis of iron and nickel. Sulfur and oxygen could also be present here and it gets to be about 4,000 degrees Celsius. We move on to level C, which is turning a little bit reddish. We have the mantle, which this is the largest part and the most complex layer of Earth. Most of the upper part of the mantle is solid rock, but temperatures here can reach about 1,000 degrees Celsius. The temperatures in the lower area of the mantle are approximately 2,500. So if you go closer to the center, it's hotter, and then outer is cooler. Not cool at all though, it's 1,000 degrees. Damn. Hope you don't touch it, by the way. It's very hot. All right, and finally we're at D. This is where we live, the crust. Okay, we live on the thinnest part, the crust. Wow, could you believe it? The crust is on the outside of Earth, and it's the thinnest layer, and it continues under the oceans. Let's break down the crust a little bit more. So within the crust and upper mantle, you have the lithosphere and asthenosphere. The lithosphere is a rigid layer of Earth consisting of the crust and upper mantle. It's broken into 12 large plates that can move. Now, some of you geniuses out there know that the plates move. The asthenosphere is the semi-molten zone of the mantle, just below this lithosphere. Now, the way I explain this to my kids is the lava, actually called magma in Earth, is like water. Okay, just think about it as water. Now the water is moving. Sitting on top of the water are boats. Those boats are land, the continents of Earth, the lithosphere. The lithosphere are the continents that float on the lava or magma, and they keep moving around. They don't stay in one spot. If you ever went on a kayak and you went into the ocean, I was at Tofino one time, and me and my broski were sitting on there, and we like, oh, we're so tired, we're gonna take a break. So we put the paddle down, and we just kind of rested our eyes for a bit. We laid down. We woke up a bit later, and we were so far into the ocean that we got a little bit scared. How did we get there? Well, you're floating on water. The water has a current that moves the land. Very little at a time, but it does move. As you can see here, we have different plates. There's 12. The Pacific Plate, North American, Eurasian, the Nubian, just to name a few. Convection currents. The currents within Earth. Convection current is the movement of the plates. It's rising of warm material, cooling, and then sinking down. Hotter rock rises, just like hot air rises, and cooler rocks sink, just like cold air. And then the plates of the lithosphere are moved by these melted rocks. Here's a diagram. You have the inner core. Remember, the core is 5,000 degrees, super hot. So when the molten rock comes down here, it gets heated up by the core and then rises up, just like hot air rises. Once it gets to the surface, the cold atmosphere and outer space cools down the mantle rock, which then becomes more dense. As you know, dense material sinks, so it begins to sink back down to the inner core, or outer core, sorry. The core then heats it up again at 5,000 degrees, and it is again lifted up. Earth's magnetic field. What is a magnetic field? It's a region a force around a magnet. The purpose of Earth's magnetic field is to protect Earth from dangerous radiation from the sun. We're gonna watch a couple videos here that explain what Earth's magnetic field is all about.
Compasses show directions, but how do they actually work? Compasses have a freely spinning needle, which is a magnet. As the Earth is a giant magnet, the compass and the Earth act as any two magnets do. The north pole of the compass is attracted to the south magnetic pole of the Earth. Now this is a rather confusing part. The North Pole, geographically as we think about it, is actually a south magnetic pole. But all you really need to know is that the Earth is a giant magnet, which is why we can use compasses to show us which way north is. Did you know that the North Pole is not the same as the magnetic north, as the North Pole is determined by the Earth's spin and the magnetic north by the direction a compass points? However, unlike any ordinary magnet, the magnetic Earth's poles can switch. So the North Pole becomes the south and the South Pole becomes the north. This pole reversal has actually happened many times before and is likely to happen again soon. In fact, in the last 20 million years, it has switched every 200,000 to 300,000 years, which is quite often considering how old the world actually is. The proof for this magical reversal is right at the bottom of the ocean, on either side of the mid-Atlantic rift. As rising lava here solidifies, it becomes permanently magnetized in the direction of the Earth's magnetic field. And, by taking sediment cores from the surrounding ocean floor, scientists are able to see bands from the switching poles. You might now be wondering, how on Earth, quite literally, can such a phenomenon occur? Geophysicists aren't entirely sure. However, they think it's something to do with the Earth's soft iron core being surrounded by hot, liquid metal, and the electric currents produced within this layer. So does the Earth being a giant magnet do anything useful? Well, it plays a big part in maintaining Earth's atmosphere. Solar wind is a flow of charged particles coming from the sun. The Earth's magnetism usually protects the surface of the Earth from these particles, but if some manage to get through, then we could see the aurora, also known as the northern lights. If there was no magnetic field, the solar wind would strip away the Earth's atmosphere, leaving the Earth's surface exposed to the damaging UV light rays from the sun. Interestingly, this gives rise to one theory about why Mars barely has an atmosphere. If its magnetic field was switched off somehow, then its atmosphere would have been broken down by the solar wind.
Super cool stuff. So that was chapter 3.7.1, okay, 1 of 3 in chapter 7. Today we talked about the model of Earth and its layers. We talked about the crust, the mantle, the outer core, the inner core, 4 main layers. Okay, the lithosphere that is broken down into 12 large plates that can move, and convection currents that help the movement of those plates within the asthenosphere and the lithosphere.